Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest and most mesmerizing questions physics has ever asked. Is the universe actually two-dimensional? Could it be that everything you see, feel and move through, your room, your city, the stars above, might be in some profound sense just a kind of grand projection from a surface that lives at the edge of reality? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the universe's dimensions together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. When you think of your everyday life, you move in three familiar directions: forward and back, left and right, up and down. That's what we call three dimensions. They give you the space to stretch your arms, walk across the floor, or look up at the ceiling. Add the slow, steady flow of time, and you have what most people call the stage of reality. 3 dimensions of space and 1 of time. Simple, solid, dependable. Yet, deep within physics lies the suspicion that this stage might not be as solid as it appears. The script of the universe may be written in fewer lines than the play itself suggests. Imagine for a moment the shadow of your hand on a wall. The shadow looks two-dimensional, a dark patch on a flat surface. But behind it is your 3-dimensional hand moving in richer ways. Now, flip the thought around. What if we, our stars, our galaxies, our entire universe, are the shadow? What if the real writing, the true code, is traced not in our familiar 3 dimensions, but on some distant surface, like the wall on which the shadow falls? This is the essence of what physicists sometimes call the holographic principle, and it begins with a strange and beautiful clue: black holes. These mysterious objects, once thought to be silent cosmic vacuums swallowing everything whole, turned out to whisper something subtle about entropy, information, and surfaces. They seem to say, the amount of information inside a region doesn't scale with its volume, it scales with its boundary. It was as if the universe were hinting that its secrets are written on walls, not in the air within. But before we get too far ahead, let's soften the ground with a slower thought. Take a glass of water. Imagine placing an ice cube into it. Over time, the cube melts, the water warms, the balance shifts toward evenness. That gentle, unavoidable drift is the work of entropy, the measure of disorder, or perhaps more kindly, the measure of how many ways things can be arranged. Entropy is what pushes the arrow of time forward, what makes your tea cool, what makes your room get messy if you don't keep tidying it. It's ordinary, but it's also the whisper of cosmic law. And strangely enough, entropy is what links steam engines in the 1800s to black holes, to holograms, and to the thought that our universe might be two-dimensional at heart. If this seems like a leap, don't worry, we'll walk it slowly. Think of it as a nighttime stroll, where each streetlight is one more clue, one more gentle step toward understanding. First, we'll wander back to the world of thermodynamics, when physicists puzzled over engines and heat, discovering that no machine can be perfectly efficient because entropy always grows. Then we'll pause by the desk of Ludwig Boltzmann, who looked at the world and saw not just steam and pistons, but a dance of countless particles, each contributing to the grand tendency toward disorder. From there, we'll drift into the starry night where black holes reign, and we'll listen carefully to the message they send us through their event horizons. Information seems to cling to surfaces, not to the depths we imagine. Along the way, we'll step lightly into metaphors that are easier to rest with. A soap film stretched across a wire frame will show us how geometry and information link together. A shuffled deck of cards will show us why entropy grows. A credit card hologram shimmering with rainbow light will show us how three-dimensional images can be encoded on flat plates. And eventually, we'll arrive at the boldest proposals of modern physics, that the universe we live in is, in a precise sense, like a hologram, its fundamental description written not in the depths of space, but on its distant boundary. Of course, we'll also keep our balance. It's important to say that none of this is proven for our actual universe. ADS-CFT, the most concrete example of holography, works in a kind of universe that is not ours. A universe with negative curvature, shaped like a bowl rather than a balloon. Experiments like the Fermilab holometer have searched for hints of holographic noise and come up empty. So, we remain in a space of questions, not of certainties. But questions themselves can be soothing, like stars overhead, not grasped but admired. So tonight, let this thought guide you gently. Dimensions are not as rigid as they appear. A square folds into a cube suggests a hypercube, and perhaps our three-dimensional world folds into a two-dimensional script beyond our sight. Whether or not it is true, the very act of wondering reminds us how delicate, how mysterious, and how beautiful the universe really is. If you've ever folded a piece of paper into a small square, you already know something about dimensions. A line is one-dimensional. You can only walk along it. A square is two-dimensional. You can move forward and sideways. Fold the paper into a cube, and suddenly you have three dimensions. Height joins length and width, giving you room to breathe, walk, and stretch. Each new dimension feels like an invitation, a new axis to explore. But what if you kept going? What if you could fold again, stepping into a fourth spatial dimension? That idea has long teased mathematicians and dreamers alike. The cube's four-dimensional cousin is called the tesseract or hypercube. You can't hold one in your hands, but you can project it, the way a cube shadows a square. Artists and mathematicians often draw a cube inside another cube, connected by lines, as if the outer one is the shadow of a deeper, invisible shape. Staring at it can be unsettling. It looks familiar but wrong, like a room tilted in a way your body doesn't understand. The thought of hidden dimensions is not new. In the Victorian era, writers and philosophers were captivated by it. The 19th century was a time of discovery, of trains shrinking distances and telegraphs shrinking time. It was also a time of deep curiosity about what might lie beyond the visible. Some writers imagined spirits inhabiting unseen dimensions. Others, like Edwin Abbott in his novella Flatland, told playful but profound stories about two-dimensional beings discovering the shocking existence of up. To the residents of Flatland, a circle is all they can see of a passing sphere. To them, the sphere is a miracle, an incomprehensible intrusion from a direction they can't imagine. Later, H.P. Lovecraft would take this fascination into darker realms. His stories sometimes hinted at alien beings whose shapes made no sense, whose angles seemed wrong, whose existence suggested dimensions humans could not safely grasp. These stories were less about mathematics than about the deep unease that comes from realizing our perspective may be only partial. Behind every corner of reality there might be a direction we cannot look. But this isn't just the realm of fiction. Physicists too wondered about hidden dimensions. In fact, modern theories like string theory require extra dimensions, sometimes 6, sometimes 7, tucked away so tightly we never notice them. They are curled, compact, like garden hoses seen from afar. From a distance they look like simple lines, but up close they reveal loops and curves. Why does all this matter for our question tonight? Because thinking about dimensions trains the mind to accept that what seems absolute might be negotiable. Just as Flatlanders couldn't imagine up, perhaps we can't imagine the true blueprint of our universe. What if our three-dimensional world is itself a projection? The way a shadow is a flattened glimpse of a higher truth? Or what if it is the other way around, that our three dimensions are not fundamental at all, but arise from information written on a two-dimensional boundary? This is where mathematics and imagination meet. Consider again the shadow of your hand on the wall. The shadow is a two-dimensional image of your three-dimensional hand. But everything about your hand, the curve of your fingers, the distance between them, is encoded in the shadow's outline. With enough information, someone clever enough could reconstruct the hand from its shadow. Similarly, a hologram etched on a flat surface can, when lit properly, reconstruct a full three-dimensional image. You tilt a credit card in the light, and suddenly a dove or a globe seems to float above it, shimmering, alive. The card itself is flat, but it contains the instructions for depth. Physicists looked at this and wondered, what if the universe itself is like that? What if the deep reality is simpler, two-dimensional, and our three-dimensional lives are the projection? It is a strange thought, and yet it seems less absurd once you notice how often nature prefers surfaces over volumes. Think of a bubble blown from a soap wand. The bubble is a thin film, its surface shimmering with colours. Inside is just air, not much at all. But the surface contains all the action, the tension that holds it together, the rainbow interference patterns, the fragile beauty. What if the universe is like that? A three-dimensional stage floating out of a two-dimensional script, with the real information clinging to the edges. Of course, the universe does not announce its secrets in plain words. It leaves us hints, scattered like breadcrumbs. Black holes whisper one such hint. Their entropy, their information content, scales not with how much space they contain, but with the area of their surface. It is as though the universe is reminding us softly but firmly that surfaces matter more than we expect. But before we dive into black holes and their strange thermodynamic lives, it helps to pause with the idea of entropy itself. Entropy began not in the stars but in the steam engines of the 19th century, when engineers puzzled over why no machine could ever be perfectly efficient. Heat always seemed to leak away, order always seemed to decay into disorder. What began as a practical question about locomotives became, over decades, a profound insight about time, information, and perhaps even the shape of the cosmos. So, as we move forward, think of dimensions as doors. 3 are open to us. Others might be locked. Some may not exist at all. And yet, by watching shadows and listening to surfaces, we may find that the universe has been hinting at a hidden script all along. To understand why physicists even began thinking about entropy, black holes, and information, we have to go back to a time of iron rails, coal smoke, and the rhythmic sigh of steam engines. The 19th century was the age of steam, when locomotives shrieked across the countryside and factories pulsed with new power. But behind the excitement of this mechanical revolution was a quieter puzzle. Why were machines never perfectly efficient? Why did so much energy, despite clever engineering, slip away as waste heat? Enter Nicolas Léonard Sadi-Carnot, a French engineer who, in 1824, asked the question with rare clarity: what are the limits of an engine? He imagined an idealized heat engine and showed that efficiency always depends on the temperature difference between the hot source and the cold sink. No matter how perfect the engine, some heat would inevitably flow into the cold reservoir. Perfection was impossible. Waste was unavoidable. This was the birth of a new kind of thinking, thermodynamics. It wasn't about pistons and gears anymore, but about fundamental laws. A few decades later, Rudolf Clausius would give the elusive phenomenon a name: entropy. He declared, with stark simplicity, the entropy of the universe tends to a maximum. It was a sobering sentence hinting that the cosmos itself had an arrow, pointing not toward greater order, but toward greater disorder. But disorder is a cold word, so let's soften it. Imagine you're making tea. You pour boiling water into a mug, dip the bag, and then set it aside. At first, the water is scalding hot, the room around it cooler. Slowly, inevitably, the temperatures approach each other. Heat flows out of the tea, warming the air slightly, cooling the drink. The tea never gets hotter on its own. This gentle balancing act is entropy at work. It's not destruction, but a tendency toward evenness, a smoothing out of differences. Or imagine an ice cube dropped into that same cup. You hear the faint crack as it meets the hot water. Slowly, the cube dissolves into the liquid, its ordered structure of molecules dispersing. The ice doesn't spontaneously reassemble, no matter how long you wait. The arrow of entropy runs one way. It is as if nature has a preferred direction, an insistence that things should mix, spread, and equalize. This idea was not just about tea or ice cubes. It was about time itself. Entropy gave time its arrow. Without it, physical laws are strangely symmetrical. An equation that describes two billiard balls colliding works the same way forward or backward. But entropy is not symmetrical. It increases. It tells us why eggs break but don't unbreak, why smoke disperses but never gathers back into a neat ball, why we grow older but never younger. Entropy is the reason your memories are of the past and not of the future. In the quiet of a Victorian laboratory, amid brass instruments and ticking clocks, these realizations took root. Clausius, William Thomson, better known as Lord Kelvin, and others debated the implications. If entropy always grows, what about the universe itself? Would it one day run out of differences altogether, fading into a featureless equilibrium? The phrase heat death was whispered. A future in which all stars burned out, all temperatures equalized and no structure remained. A haunting thought, and one that lingers even now. Yet for all its inevitability, entropy was also liberating. It gave engineers practical rules, allowing them to design better engines, refrigerators, and power plants. It tied human industry to cosmic destiny. The coal that powered a train was subject to the same law as the stars burning overhead. The puff of steam from a locomotive was a microcosm of the universe's grand drift toward balance. This was just the beginning, though. For while entropy explained the arrow of time, it left a question dangling. What exactly is entropy made of? Clausius gave it a name, but it was Ludwig Boltzmann who peered deeper. He imagined atoms and molecules, countless unseen particles jostling and colliding. To him, entropy wasn't just about heat flowing. It was about probabilities. A system with low entropy is like a tidy room, possible, but rare. A system with high entropy is like a messy room, overwhelmingly likely, simply because there are so many more ways for things to be disordered than ordered. Think again of that tea. The hot molecules bounce around wildly while the air molecules move more slowly. When the two meet, collisions spread the energy. Eventually they share a common temperature. This isn't magic, it's statistics. There are vastly more ways for the molecules to share energy evenly than for them to keep it uneven. Entropy is simply the universe playing the odds. In the soft glow of gas lamps and candlelight, Boltzmann inscribed a formula on paper. S, just K log W. Entropy, S, is proportional to the logarithm of the number of microstates, W. It was the key that unlocked the microscopic meaning of Clausius's law. Each arrangement of particles is a microstate, and entropy is the grand count of how many are possible. The more possibilities, the greater the entropy. Boltzmann's insight was profound, but also unsettling. It said that order is fragile, rarity against the tide. Disorder is not a flaw, but the natural drift of chance. For some, this felt nihilistic, but for others, it was oddly comforting. Entropy was not an enemy. It was simply the measure of possibility, of how many ways the world could be. As you sit here tonight, perhaps wrapped in a blanket, think of entropy not as something ominous, but as a quiet leveling. It is the reason your tea cools, the reason your room fills with the smell of baking bread, the reason stars shine and eventually fade. It is, in a sense, the universe's way of sharing, and it is this very principle, born from steam engines and tea, that will lead us to black holes, holograms, and the possibility that our three-dimensional lives are shadows cast from a deeper script. Picture yourself in a quiet room with a deck of cards. You shuffle once, twice, a dozen times, lay the cards out on the table, and what do you see? Almost, always, a jumble. The suits are scattered, the numbers out of order. If you shuffled for the rest of your life, you might never see them fall into perfect sequence. Ace through king, 4 suits in neat rows. It's not impossible, but it is so staggeringly unlikely that the universe itself seems to lean away from it. This, in a gentle way, was Ludwig Boltzmann's great insight. He realized that entropy is really about likelihood. Order is rare, disorder is overwhelmingly probable, and probability, not some hidden cosmic preference, is what gives the arrow of time its push. In Boltzmann's day, the very existence of atoms was still debated. Many thought matter was smooth, like clay or honey, infinitely divisible. Boltzmann insisted otherwise, that everything is made of tiny particles, countless in number, always in motion, colliding and scattering like dice across a table. Tracking each particle was impossible, but you could understand the whole by asking what is most likely. Entropy, he suggested, is simply the count of how many microscopic arrangements can produce the same macroscopic appearance. A glass of warm water looks calm and ordinary, but behind the scenes the molecules are darting, swirling, colliding in endless ways. There are billions upon billions of possible patterns of movement that all feel, to your hand, like warm. That abundance of hidden possibilities is entropy. Let's soften this with a room. A perfectly tidy bedroom has only a few acceptable arrangements: books stacked, clothes folded, papers aligned. But a messy bedroom, there are countless ways to scatter socks, topple books, and pile laundry. Disorder is not special, it is simply more probable. The universe doesn't choose mess, it just falls into it, because mess has more ways of existing. This way of thinking reshaped everything. Suddenly the second law of thermodynamics wasn't a stern rule etched in stone, but a gentle statement of odds. Systems evolve toward higher entropy, because there are more ways to be disordered than ordered. The future is simply the direction in which possibilities multiply, and from that came something deeper, the arrow of time itself. Imagine filming 2 billiard balls colliding. Run the film forward, then backward. They look the same. But now imagine an ice cube melting in water. Run that film backward and you instantly know it's wrong. Why? Because entropy decreases in the reversed film, and that is so improbable it jars the mind. Time's direction, Boltzmann showed, is nothing more than the natural tilt toward probability. There's a quiet poetry here. The reason you remember yesterday and not tomorrow is because yesterday was lower in entropy. Its details were still intact, fewer, rarer. Tomorrow, those details will be scattered into a vastness of possibilities, too abundant to recall in advance. Memory, like the rest of life, points in the direction of entropy's climb. Boltzmann even imagined fluctuations, rare, reversals, tiny local dips in entropy that might briefly create order out of chaos. He speculated that perhaps our world, our very lives, are such a fluctuation, a rare oasis of structure in a sea of disorder. It was a radical idea, unsettling but bold. And though not all agreed, the image of an improbable island of order floating in a wider ocean of chaos still stirs thought today. Of course, his ideas were not universally welcomed. Some found the talk of chance and probability too unsatisfying, too abstract. Boltzmann himself struggled against resistance. Yet history proved him right. Atoms are real. Molecules do dance, and entropy truly is the mathematics of likelihood. So tonight, as you rest, Imagine the universe as an endless shuffle of cards or a pair of dice tumbling across a cosmic table. The odds lean toward disorder, not out of malice, but out of abundance. Entropy is not the end of stories. It is what makes stories unfold. It is the reason tea cools, the reason stars shine, the reason time itself whispers forward. And in that whisper, Boltzmann gave us a profound gift. The understanding that behind every ordinary moment, every shuffle, every breath, every sigh, there lies a hidden vastness of possibilities, and it is those possibilities that carry us gently from past to future. Time is a curious thing. You can look at a clock and see its hands sweep forward. You can feel your body grow older, moment by moment. You can watch a sunset fade into night, then dawn return again. But beneath all these rhythms, the laws of physics themselves, the equations describing particles and forces, don't really care which way time runs. A collision between two billiard balls looks the same if you run the film backward. The orbit of the planets can be calculated equally well in either direction. On paper, time is reversible. And yet in life, time feels anything but reversible. You remember breakfast but not tomorrow's dinner? You can scramble an egg, but you cannot unscramble it. You can burn a piece of paper, but you cannot make the ashes leap back together into a letter. The flow of time has a direction, and entropy is the quiet whisper that explains it. Entropy grows. It is the one quantity in physics that seems stubbornly one way. Once you see it, you cannot unsee it. Pour cream into coffee, and the two swirl together into a blended brown. You might stir it, but it never unstirs. The reason is not that molecules are forbidden to separate again. It's that the odds against it are overwhelming. There are trillions upon trillions more ways for the molecules to mix than to separate. So entropy increases, and in its increase, we sense the passage of time. Think of your own memory. You remember the past because it is the low entropy side of the slope. Once events have scattered, once they have spread into countless microstates, they can no longer be reassembled. Your mind, like everything else in the universe, is carried forward by the tide of increasing entropy. You live in a world where eggs break, tea cools, stars burn, and galaxies drift apart. You cannot go back because entropy has already stepped forward. This gives the universe its arrow, not an arrow drawn on a map, but an arrow stitched into the very fabric of experience. Entropy doesn't just measure disorder, it measures possibility. And the future is always more possible than the past. Imagine a library filled with books. If every book must sit in one specific spot, there are very few ways to arrange the shelves. But if the books can be anywhere, lying sideways, piled in corners, stacked on chairs, the possibilities multiply without end. That's entropy. The neat library is the rare, low entropy state. The sprawling mess is the high entropy state. The world drifts toward the mess, not because it prefers mess, but because there are vastly more ways to be messy than tidy. Extend this image to the cosmos. The early universe, moments after the Big Bang, was remarkably ordered. Smooth, hot, dense, but with relatively low entropy. Like a library with all its books stacked neatly, its possibilities were few. As the universe expanded, it opened up more and more ways to arrange itself. Stars formed, galaxies spun, black holes yawned open, entropy rose, and it still rises. Every day, with every breath you take, with every star that burns its fuel, entropy increases, and the arrow of time points forward. It might sound bleak, this march toward disorder, this gradual smoothing into balance. But there is a gentle comfort hidden in it too. Without entropy, there would be no flow of time, no unfolding of moments. Without entropy, you could not grow, laugh, learn, or remember. The very fact that the past is different from the future is what makes stories possible. Entropy is not the villain, It is the narrator, whispering the tale of existence page by page, and there is more subtle beauty. Though entropy grows, it does not erase structure immediately. In fact, it often creates pockets of order along the way. Stars form by collapsing gas clouds. Planets condense. Life itself emerges as an intricate way to channel energy and increase entropy around it. Your body, sitting here listening, is a kind of entropy machine. You take in food, you burn it for energy, you radiate heat. You're a little whirlpool of order in a vast river of disorder. That is not a contradiction. It is exactly how the laws allow complexity to bloom, even in a universe destined to even out. So when you see cream swirling into coffee, or watch the last ice cube melt in your drink, you're not only witnessing physics, you are watching time itself. That slow blending, that one-way flow, is the same arrow that carries you from childhood to adulthood, from sunrise to sunset. It is the same arrow that carries galaxies apart across billions of years. Physicists call it the thermodynamic arrow of time, but you can think of it more gently. It is time's whisper, soft but insistent, guiding all things forward. You don't have to feel its equations to sense its truth. You only have to live a day, to recall a memory, to breathe, to see that yesterday is behind you and tomorrow is ahead. And here is the quiet marvel. This law, born from the engines of the 19th century and sharpened by Boltzmann statistics, stretches all the way to the edge of black holes, to the horizon of space-time itself. Entropy, which explains the cooling of tea and the shuffling of cards, also explains why black holes are not just emptiness, but thermodynamic systems. They have temperatures, entropies, and even information encoded on their surfaces, and it is there, at the edge of a black hole, that the universe begins to whisper something even stranger. Perhaps everything is written on surfaces, but we're not quite ready for black holes yet. Before we step into their shadows, let us linger a little longer with entropy itself, letting its whisper sink in. It is not a monster or a thief. It is a tide carrying us forward. And though it cannot be reversed, it can be understood. And in that understanding, there is a kind of peace. Black holes have always carried a kind of mythic weight. To most people, they are cosmic monsters, bottomless pits that devour light and swallow stars whole. But when physicists studied them more carefully, they discovered something stranger. For all their ferocity, black holes are astonishingly simple. In fact, they are some of the simplest objects in the universe. This realization became known as the no-hair theorem. The phrase might sound odd, but its meaning is plain. Black holes have no hair, no extra features, no messy details clinging to them. All that matters are three numbers: their mass, their electric charge, and their spin. That's it. You could collapse a mountain, a star, or a whole library into a black hole, and from the outside you would learn nothing about what it once was. The black hole would show you only its weight, whether it was charged, and how fast it was rotating. Think of it like a safe. If you place your most personal treasures inside, letters, photographs, jewellery, the outside world sees none of it. They see only the safe itself, its size, its heaviness, perhaps the gleam of its lock. The contents are hidden, irretrievably private. Black holes are like that. The treasures are gone from view, sealed behind an event horizon that reveals almost nothing about what went in. This simplicity is jarring, because the world around us is built on complexity. A tree has countless leaves, each with its veins and patterns. Human being has memories, fingerprints, a unique laugh. Even a stone has mineral grains, tiny differences that make it distinct from another. But collapse any of these into a black hole, and the individuality vanishes. What was once richly detailed is now represented by a handful of numbers. John Wheeler, the American physicist who gave us so many evocative phrases, summed it up. Black holes have no hair. It was a playful way of saying that all the little distinguishing features of matter are stripped away and collapse. The black hole is bald, smooth, indifferent to its past. There's something both eerie and oddly comforting about this. On one hand, it feels like a kind of cosmic erasure. All the details of a star's life, its flares, its convulsions, its centuries of burning, are wiped clean when it collapses into a black hole. On the other hand, it is beautiful in its simplicity. The universe, so messy elsewhere, has carved out places of absolute clarity. But simplicity can be misleading, for behind that smooth exterior lies a puzzle. If black holes are so bare, what happens to all the information about what fell into them? Does it vanish? Can the universe truly erase details so completely? These questions would lead physicists into decades of debate, and eventually to the discovery of holography itself. For now, imagine standing by the edge of such an object. Not that you could, but just in thought. A star has collapsed, its light gone, its heart compacted to a point. Around it stretches the event horizon, the invisible boundary past which nothing returns. From the outside, you see only darkness. Yet you know that within, matter has fallen, compressed into something unlike anything else in physics. And here's where the safe analogy begins to falter. With a safe, you could, in principle, open the lock and recover the contents. With a black hole, the horizon is absolute. Once something crosses it, there is no coming back. Not for matter, not for light, not for whispers of information. From the outside, you have no access to what lies within. It is sealed more thoroughly than any human lock could ever manage. This raises deep unease. Our physical laws, especially those of quantum mechanics, say that information should never truly be lost. Shuffle it, scatter it, disguise it. Yes, but erase it forever? No. And yet, the no-hair simplicity of black holes seems to suggest exactly that. Drop a library into a black hole, and you cannot tell from the outside whether it was filled with poetry or blank pages. All you can measure is the weight of the safe now sitting behind the horizon. Physicists like to probe the universe with metaphors, and black holes respond with metaphors of their own. They are both prisons and mirrors, both erasers and record keepers. Their simplicity is their mystery. And perhaps that's why black holes fascinate us so much. They are cosmic riddles written in plain ink. Mass, charge, spin. The rest is silence. But silence in physics is rarely the end of the story. Often it is a prelude, the stillness before a deeper truth is revealed. In the sessions ahead, we'll see that this deceptive simplicity hides something remarkable. Jacob Bekenstein will suggest that black holes, though bare, have entropy, measure of hidden information. Stephen Hawking will show that they glow faintly, radiating heat into the cosmos. And together, their work will transform black holes from cosmic vacuums into thermodynamic beings, creatures of entropy and information. For now, though, let the thought settle. Black holes, the most extreme objects in the universe, are paradoxically the simplest. They are safes that reveal only their weight. They are shadows that strip away the details of what cast them. They are bald, smooth, silent, and yet, somehow, they whisper the next chapter of physics. In the early 1970s, a young physicist named Jacob Bekenstein began to wonder about the very thing that made black holes so unsettling: their silence. If they really were the ultimate locked safes, erasing every trace of what fell in, then something was missing from our understanding. Physics had already taught us that entropy is everywhere, tied to every system with heat and motion. Why should black holes be an exception? Entropy, remember, is the measure of how many possible microstates lie hidden behind the scenes of a system. A hot cup of tea has high entropy because there are countless ways its molecules can arrange themselves while still producing the same average warmth. A neatly stacked deck of cards has low entropy because only a few arrangements count as ordered. Entropy is always there, waiting in the background, a reminder that complexity hides behind the curtain of appearances. Bekenstein asked, shouldn't black holes have entropy too? After all, they seem to erase information, swallowing distinctions without a trace. If entropy is the measure of hidden information, then black holes, of all things, ought to have a great deal. At first, the idea seemed impossible. Entropy usually grows with volume, with how much space you have to arrange things in. But black holes are defined by their event horizons, surfaces that seal off the interior. If there were entropy, where would it live? Bekenstein's leap was to suggest that it lives not inside, but on the horizon itself. He proposed that the entropy of a black hole is proportional not to the volume it encloses, but to the area of its surface. That was radical. It was as if the universe was saying, the measure of hidden information doesn't grow with depth, but with surface. Think of a library again. Normally you'd expect its information to be in the books on the shelves, filling the volume of the room, but in Bekenstein's view, it's as though the essential catalogue of that library were written on the walls outside. You don't need to open the doors and walk among the shelves, the surface tells you the count. Or picture the mosaic tiles of a bathroom wall. Each tile might hold one bit of information. The larger the wall, the more bits you can place. For black holes, the tiles are unimaginably tiny, Planck-sized squares, smaller than anything we can physically picture. Yet the rule is simple: add more surface, gain more entropy. Each new Planck tile represents another possible configuration of information. This proposal didn't just fill a gap, it planted the seed of something much bigger. Because if black holes really follow this surface law, then maybe the entire universe does. Maybe the true accounting of information is written on boundaries, not volumes. The holographic principle, decades later, would bloom from this seed. But Bekenstein's idea was not accepted easily. Some physicists balked. It sounded too neat, too strange, too unlike anything else in physics. And yet it carried a compelling logic. Black holes seemed to defy the second law of thermodynamics, throw in a hot object with high entropy, and from the outside it looked like entropy had simply disappeared. That couldn't be right. To preserve the second law, black holes themselves had to carry entropy, enough to balance the books of the universe. Bekenstein even suggested that the entropy of a black hole was proportional to its area divided by the square of the Planck length, the smallest meaningful unit of distance. This would mean that the smallest possible patch of surface corresponds to the smallest possible chunk of information. One tile, one bit. A cosmic accounting system woven into geometry itself. At the time, this was speculation, a bold guess, but it was soon to find dramatic confirmation. Stephen Hawking, working with the equations of quantum fields near the event horizon, discovered that black holes aren't perfectly black at all. They emit a faint glow, radiation that carries away mass, slowly evaporating the black hole. And in Hawking's equations, the temperature and entropy matched Bekenstein's prediction precisely. But let's pause before we get to Hawking. For tonight, it's enough to dwell with Bekenstein's leap, that entropy clings to surfaces, not volumes, that the area of a horizon counts the hidden possibilities of matter and energy within, that the smooth blackness of a hole is not empty, but encoded with a richness of unseen information. It's a thought that bends the mind. We expect the richness of the world to live inside things, in the library's books, in the safe's contents, in the heart of a star. Bekenstein suggests otherwise. He invites us to look at the surfaces, at the skins, at the edges. There, in the delicate measure of area, the secrets are stored. Tonight, you might imagine your own room this way. Not by the furniture inside, not by the volume of air you breathe, but by the walls themselves, the boundary that encloses it. As if all the stories of what's inside could be written on the paint, brick, or wood. It's not how we usually think, but then neither is physics. And so, the story of black holes takes its next step. From Wheeler's bald simplicity to Bekenstein's daring proposal, we move from silence to a whisper of information. A whisper written not in volumes but in areas. A whisper that will soon, thanks to Hawking, become a glow. When Jacob Bekenstein proposed that black holes have entropy, many found it unsettling but elegant. Still, there was one missing piece. Entropy is tied to heat, and heat is tied to temperature. Could a black hole, the coldest of objects, truly be thought of as having a temperature? Was it possible for something that swallows everything to give anything back? Enter Stephen Hawking. In 1974, working late nights with chalkboards and quantum equations, he discovered something astonishing. Black holes are not perfectly black. They glow. The glow is faint, almost ghostly. To understand it, imagine space near the event horizon, the invisible boundary beyond which nothing can escape. Quantum mechanics tells us that empty space is not truly empty. It seethes with fluctuations, particles and antiparticles bubbling into existence for the briefest instants before annihilating each other. Normally these pairs cancel and vanish, but near the horizon of a black hole something different can happen. One particle falls in, the other escapes. To a distant observer it looks as though the black hole itself has emitted a particle, a whisper of light. This emission, now known as Hawking radiation, gives the black hole a temperature. The larger the black hole, the colder it is, because its surface is stretched over a wider horizon. Tiny black holes would burn hotter, radiating more quickly, but the giant ones formed from stars glow so dimly that the effect is nearly impossible to detect. Still, the principle is clear. Black holes radiate. They are not eternal prisons. They evaporate, shrinking ever so slowly until in theory they vanish altogether. This was a revelation. It confirmed Bekenstein's bold leap. If black holes have temperature, then they must have entropy, and their entropy is proportional to their horizon's area. Hawking's equations gave the precise factor: 1/4 of the area divided by the Planck length squared. In that simple formula, the worlds of gravity, quantum mechanics, and thermodynamics met in a breathtaking unity. But with this beauty came a paradox. Imagine throwing a book into a black hole, a book filled with secrets, stories, or codes. From the outside, all you see is the black hole's surface swelling slightly, its entropy growing by an amount proportional to the increase in area. As it radiates Hawking particles, however, what comes back is featureless thermal radiation, heat without detail, ashes without letters. This leads to the black hole information paradox. If the black hole eventually evaporates entirely, then all the intricate details of what fell in seem to vanish forever, replaced by random heat. Information, in other words, is destroyed. But this clashes with the deepest rule of quantum mechanics. Information cannot be lost. Quantum processes may scramble it, spread it, disguise it, but they cannot erase it outright. The paradox shook physics. Was Hawking right that information vanishes? Or was there some hidden mechanism, some subtle accounting system that preserves it? The debate raged for decades, with Hawking himself at first defending loss and others, like Gerard 't Hooft and Leonard Susskind, arguing fiercely that information must survive. To picture this paradox, think of burning a letter in a fireplace. The paper turns to ash, the ink curls away, the words are gone. Yet in principle, if you collected every particle of smoke, every photon of heat, every molecule of ash, you could reconstruct what was written. The information is scrambled, but not lost. With a black hole, Hawking suggested, the story might be different. The ashes, the radiation, carry no trace of the words. The message is not scrambled, it is obliterated. For physicists, this was almost intolerable. The laws of nature seemed to be breaking their own promise. To lose information would be to unravel the consistency of quantum theory itself, and so, black holes became battlegrounds for some of the deepest debates in science. Were they information destroyers? Or was their simplicity hiding a more subtle truth, a holographic layer on which every detail was preserved. The irony is striking. Black holes, once thought to be the ultimate dead ends of physics, turned out to be fertile beginnings. They forced us to rethink what entropy means, how surfaces carry information, and whether the universe itself might be encoded like a hologram. Hawking's discovery of radiation, born from the cold equations of quantum fields near horizons, became the warm spark that lit a fire under theoretical physics. Tonight, as you imagine the cosmos, think of black holes not just as dark voids, but as faintly glowing coals. Each one radiates softly into the night, its life measured in a slow dwindling. They are not eternal, but mortal. They shine with the quiet heat of entropy, whispering that even the most powerful prisons leak light. And in their glow lies a mystery still unsolved. Is the information of the universe safe, hidden somehow on the surface tiles of the horizon? Or does it dissolve into nothing, vanishing as the black hole fades away? That paradox is not only a puzzle for physicists, it is an invitation, a doorway to the idea that maybe the universe itself is holographic. Once Bekenstein and Hawking had shown that black holes carry entropy, a new question naturally arose. How much? If entropy is the measure of hidden possibilities, then what are we really counting when we speak of a black hole's secrets? Physicists began to picture the event horizon, the invisible boundary of a black hole, not as smooth and featureless, but as a kind of ledger. Imagine it like the tiled wall of a bathhouse, covered not in ceramic squares but in unimaginably tiny tiles. Each tile represents one unit of information, one yes or no choice, one whisper of what has passed beyond the horizon. The bigger the surface, the more tiles it can carry. How small are these tiles? To give you a sense, they are not the size of atoms, not the size of protons, not even the size of the quarks inside protons. They're far smaller than anything we can truly picture. Physicists call this smallest possible unit of length the Planck length. It is so tiny that if you blew up a single atom to the size of the known universe, a Planck length would still be smaller than a grain of sand inside it. It is the pixel of reality, the point beyond which space and time cannot be subdivided any further. Now imagine covering the surface of a black hole with these Planck-sized tiles. Each one is like a dot of paint on a vast canvas. Alone, it says almost nothing, but together they form the record of everything that has ever fallen through the horizon. Add more tiles, and you add more capacity for information. A small black hole with a small horizon has fewer tiles, fewer possible states. A giant black hole stretching across light years has a horizon vast enough to hold a staggering mosaic of possibilities. It's a strange reversal of our intuition. In everyday life, we assume that the more volume something has, the more it can hold. A bigger jar, a bigger room, a bigger hard drive. All of them store more inside because of their depth. But black holes whisper otherwise. For them, the count of possibilities doesn't come from what's inside, but from the surface itself. The skin, not the volume, carries the secrets. To make this gentler, imagine a diary. Its words are written on the thin surface of paper, not in the empty air between the covers. Or think of a stained glass window. The beauty lies in the thin sheet of coloured glass, not in the air on either side. So too with black holes. The information lives on the surface, the horizon, not in the mysterious volume behind it. Physicists realize something even more profound. If you try to stuff too much information, too much entropy, into any region of space, the region itself will eventually collapse into a black hole. And the maximum amount of entropy it can hold is always limited by its surface, not its interior. This became known as the holographic bound, a law of nature that suggests information in the universe is always tied to surfaces, to boundaries, to skins. Picture it like filling a balloon with confetti. At first, it seems the inside can hold endlessly more, but in reality, the balloon's skin, the boundary, dictates the limit. try to cram in too much, and the balloon bursts. For black holes, there is no bursting. Instead, the boundary itself expands, calmly recording every new bit of information in fresh tiles along its surface. This vision of nature writing her secrets on boundaries feels almost artistic. Paintings live on canvases, photographs live on film, music records live in the grooves of vinyl, and perhaps the universe itself lives on surfaces, each tiled horizon a page in its grand diary. Tonight, as you imagine a black hole, don't picture it only as darkness. Picture it as a shimmering mosaic of impossibly tiny tiles, each one holding a sliver of information. Together, they make up a cosmic mural, a silent but perfect record of everything that has crossed the horizon. A mural too fine for us to read, but not too fine for the universe itself to remember. And if black holes follow this rule, perhaps the whole cosmos does too. Perhaps every horizon, every boundary, every surface in space is more than just a line between here and there. Perhaps it is a ledger, quietly keeping count. By the time physicists had come to accept that black holes carry entropy measured by their surface, an even larger question emerged. Was this surface law unique to black holes, or was it a hint of something universal? Could the cosmos itself be bound by the same rule, that information is tied not to volumes, but to boundaries? The first steps toward an answer came from Raphael Bousso in the late 1990s. He proposed what is now known as the covariant entropy bound, a generalization that applies not only to the static, steady surface of a black hole, but to the restless, expanding, curving fabric of space-time itself. In gentle terms, he argued that no matter how light bends, no matter how space stretches, the maximus amount of information that can pass through a region is always limited by the area of a certain surface surrounding it. That surface is not always obvious. In fact, it is traced out by light. Imagine lighting a lantern in the dark, its beams spread outward, tracing invisible sheets of brightness into the night. Now imagine running the film backward, lanterns not spreading light, but gathering it. These converging sheets of light, called light sheets, act as natural boundaries for entropy. Information can flow through them, but never more than an amount proportional to their area. In this way, the surface law extends beyond black holes. It says that any patch of space-time, any region at all, must respect the same rule. The information inside is never greater than what can be written on the edges defined by light. This is the holographic principle in its most general, almost poetic form. Nature counts information on boundaries, not in interiors. To make this softer, let's return to the lantern. Imagine carrying it through a forest at night. Its glow illuminates branches, leaves, and stones, creating a sphere of light around you. Everything you can see, the patterns of leaves, the roughness of bark, the scurrying of a small animal, feels rich and three-dimensional. But if the universe truly follows the holographic bound, all that richness could be described by the thin glowing shell at the edge of the lantern's reach. The surface tells the whole story. The forest feels deep, but its secrets could be written on the rim of light. This thought stretches the imagination. It suggests that depth itself may be an illusion, that the true counting of possibilities always happens at the edge. When you stand in a room, you experience its volume. But the entropy bound whispers, it's the walls that matter. When you gaze at the night sky, you see stars scattered across unfathomable distances. Yet, according to the bound, the limits of information are traced by horizons, the surfaces beyond which light has not yet reached us. Physicists are still debating what these surfaces really mean. Are they physical in the way a wall or window is? Or are they mathematical conveniences, guiding lines drawn by light? Either way, the message is consistent. Boundaries hold more weight than we once imagined. To anchor this, think again of a balloon filled with confetti. As you add more, the skin stretches, growing larger. The skin, not the inside, is what limits how much the balloon can hold. With black holes, this skin is the event horizon. With space-time itself, the skin is traced by light sheets, invisible but just as binding. Try to fit in more information than the area allows, and nature responds the only way it can, by collapsing the region into a black hole, whose surface area faithfully records the maximum entropy. There is a kind of elegance to this. It makes the universe feel economical, like an artist painting on a limited canvas. No matter how grand the picture, the edges dictate its limits, and yet within those limits the possibilities are vast. It also brings comfort. The entropy bound suggests that information is never truly lost, only constrained, written more delicately than we can yet read. Imagine a lantern beam carrying the stories of everything it touches, etching them into its glowing surface. The forest within the circle of light may seem to vanish into darkness when you move on, but the memory of it lingers on the rim of the glow. So, from steam engines to black holes, and now to the very structure of space-time, entropy has been teaching us a lesson. The universe is less about the insides than the edges. What matters most may not be the hidden volume, but the boundary that frames it. This prepares us for the next step. If information is always bounded by surfaces, then perhaps the entire universe itself is holographic, a grand projection from a cosmic boundary. But before we leap that far, it is worth pausing here, with lanterns and light sheets, with boundaries and skins, and let the thought settle. Reality may be written on its edges. Before physicists began speaking of holograms on cosmic scales, before black holes and entropy joined the conversation, there was a quieter, more earthly discovery. It came from the world of optics, of lenses and light beams, of patterns invisible to the eye, but powerful enough to store depth on a flat surface. The year was 1947. Dennis Gabor, a Hungarian-British scientist, was experimenting with ways to improve electron microscopes. He wanted to capture finer details than ordinary imaging could allow. His solution was not to take a sharper picture, but to record all the information carried by a wave of light. Not just its brightness, but its phase, the subtle timing of its peaks and valleys. If you could save both brightness and phase, you could reconstruct the wave itself, and with it, the three-dimensional image of the object that created it. Thus was born holography. The word itself means whole writing, and that's exactly what it did. It captured the whole story of the light. By splitting a beam into two parts, one bouncing off the object, the other serving as a reference, Gabor could make the waves interfere on a photographic plate. The result looked to the naked eye like a strange tangle of lines and swirls, meaningless as scribbles. But shine the right light back through it, and the interference recreated the original wavefront. Out of a flat plate, a three-dimensional image appeared, shimmering in space. If you've ever tilted a credit card under a lamp and watched a dove or a globe float above it, you've seen the principle at work. The hologram looks flat and metallic, but tilt it and depth reveals itself. A flat surface has become a window into another dimension. This was revolutionary. It showed that three-dimensional information could be fully encoded in two dimensions with nothing lost. The full depth was there, waiting to be read, stored not in thickness but in pattern. To grasp this more gently, imagine a lake at dawn. Toss in a pebble, and ripples spread outward. Toss in another, and new ripples oscillate the old, creating complex patterns. These patterns carry information about where the pebbles fell, how big they were, and when they entered the water. If you could freeze that pattern and study it carefully, you could, in principle, reconstruct the story of the pebbles. That's what holography does. It records the interference of waves, the ripples of light, and preserves the story they tell. Around the same time, another figure was quietly building the language of information. Claude Shannon, working at Bell Labs, developed the mathematical foundation of information theory. He showed that information can be measured, compressed, and transmitted, and that every signal has a kind of entropy, the measure of its uncertainty or surprise. Where Gabor gave us the technique of holography, Shannon gave us the theory of information. Together, their work hinted at a new way of thinking, that information itself might be the ultimate currency of reality. It is here that the metaphors begin to overlap. A hologram is not a picture, it is a code, an encoding of depth in patterns of light. In the same way, entropy and information are not separate from physics, they are the hidden codes behind what we see. Black holes, with their surfaces tiled in Planck squares, begin to look like cosmic holograms. Not because they project pretty doves in space, but because their surfaces encode the full depth of what lies inside. Think again of the credit card hologram. Tilt it under the light, and the image seems to leap from the surface. The card itself is thin, flat, unremarkable, yet it holds a whole volume within it. Now expand that thought. What if the universe itself is such a hologram? What if the 3 dimensions we walk through are encoded on a 2-dimensional boundary, a cosmic plate holding the ripples of reality's waves? Of course, the analogy has limits. The universe's holography is not an optical trick, but a deep principle of physics, born from entropy, black holes, and the nature of information. Still, the metaphor is powerful. It tells us that surfaces can hold depths, that patterns can hold worlds, that flatness can hide fullness. And there is something almost comforting in this. It means that the richness of experience, the sound of rain, the warmth of tea, the memory of a loved one, might all be encoded, stored, preserved, even if in ways we do not yet understand. Nothing is truly lost, only written differently. So as you let your thoughts drift tonight, imagine the quiet laboratory where Gabor first saw 3-dimensional images float above a glass plate. Imagine the shimmer of rainbow holograms on a shelf of CDs, each one a flat surface holding a hidden concert. Imagine a ripple on a pond, frozen and deciphered, telling the story of stones long gone. These are human-sized echoes of a cosmic principle, that depth can be encoded on surfaces, that boundaries can hold secrets, and that perhaps the universe itself is a hologram waiting for the right light to reveal its hidden image. When you tilt a hologram under a lamp and watch a dove or a globe float above its surface, you're witnessing an illusion, but an astonishing one. A flat plate, no thicker than a postcard, carries within it the instructions for an entire 3-dimensional image. The depth you see is not inside the plate, but written on its surface, hidden in delicate interference patterns. Physicists standing at the crossroads of entropy, black holes, and information began to ask a daring question. What if the same is true of the universe itself? What if the space we walk through, the 3 dimensions of up, down, left, right, forward, and back, are not fundamental, but emergent? What if all the richness of our world is, in some profound sense, a projection from a boundary we cannot see? It sounds outlandish, almost mystical. But the clues have been accumulating. Black holes taught us that information scales with surface, not volume. Entropy bound suggested that no region of space can hold more information than its enclosing area allows. And holography, in the optical sense, showed that surfaces can indeed encode depths without loss. Put together, these whispers began to suggest a radical possibility. Perhaps our universe is, at heart, a hologram. Let's soften this with an image. Imagine standing inside a planetarium dome. The stars overhead are not actually distant suns, but points of light projected onto the curved surface above you. And yet, when you lean back in your chair, you feel as though you were drifting in deep space. The illusion is complete. The dome holds the code, the surface holds the stars, but your eyes and mind translate it into depth. What if the cosmos works like that? What if our depth, our distances, our dimensions are the projection of information written on a distant cosmic dome? Of course, this does not mean we live in a movie theatre or on a screen. The word hologram is a metaphor, not a literal picture of our lives. What it means is that the bookkeeping of information may be fundamentally two-dimensional. Just as every point in a holographic plate contains the whole image, every patch of a cosmic boundary may contain the script for the space within. But what boundary? Where would such a surface lie? Physicists have wrestled with this question. For black holes, the answer is clear. The event horizon is the surface that encodes the interior. For the universe as a whole, the candidate is more subtle. Some propose the distant cosmic horizon, the edge of what we can see, defined by the speed of light in the age of the universe. Others propose more abstract boundaries, not physical walls but mathematical edges in higher dimensional spaces. Whichever it is, the message is the same. If the universe is holographic, then everything we know, particles, fields, even space itself, may be emergent. They may be the shadows of a deeper script, written not in volumes but on surfaces. To make this less intimidating, imagine again a diary. On its thin pages are words and sentences. The paper itself is two-dimensional, but the story you read, the characters, the landscapes, the emotions, are experienced as full, rich, and three-dimensional in your mind. The depth comes not from the thickness of the page, but from the arrangement of ink upon it. In the same way, perhaps our world is a story written on a thin surface of reality, translated by the laws of physics into the fullness of space. And yet, caution is necessary. This idea is bold, but it is not proven. Unlike the hologram on your credit card, we cannot shine a laser on the universe's edge and watch its hidden depth leap into view. The holographic principle is, at present, a guide, a framework, a beacon pointing to where deeper understanding might lie. It tells us not to take space at face value, but to look at boundaries with new respect. There is also humility in this. The thought that our three-dimensional lives might be shadows of a two-dimensional script can be unsettling, but it can also be comforting. It suggests that information, at least, is never lost, that it clings to surfaces, that it is written in the ledger of the cosmos even when hidden from our view. So, as you lie back and let your mind drift, imagine the universe as a quiet projection. Imagine yourself inside the great dome of a planetarium, stars shimmering overhead, galaxies swirling in a grand dance, all encoded on the surface above, all translated into depth by your mind. The real universe may not be so different. Surfaces may hold more than they appear. Depth may be a story, not a foundation. And in that story, every star, every atom, every memory may be written, waiting for the right light to reveal it. By the late 1990s, physicists had gathered a strange assortment of clues. Black holes whispered that information scales with surface area. Entropy bounds suggested that light sheets carry the maximum possible secrets of a region. Optical holography showed that flat plates can encode volumes. All of these hints pointed in the same direction. Surfaces matter more than depths. But whispers are not proofs. What physicists longed for was something sharper, something precise, an equation or framework where the holographic principle was not just a metaphor, but a working reality. In 1997, Juan Maldacena, then a young physicist, provided exactly that. His idea is now called the ADS-CFT correspondence, and though the words sound technical, the essence can be told gently. ADS stands for anti-de Sitter space, a kind of universe with negative curvature. If our own universe is shaped like a balloon, gently expanding with positive curvature, ADS is shaped more like a bowl, curving inward, walls rising endlessly around it. CFT stands for conformal field theory. a type of quantum theory that lives on the boundary of that bowl, on the rim that encircles it. Maldacena proposed that these two are not merely related but actually equivalent. Gravity in the bulk of the bowl is exactly mirrored by a quantum field theory on its rim. To make this softer, imagine sitting at a kitchen table with a bowl of soup. Inside the bowl, the broth swirls, complex and three-dimensional. On the rim, perhaps, are spices sprinkled in a circle. Maldacena's proposal was like saying, everything happening in the swirling broth is already encoded in the pattern of spices on the rim. Two different descriptions, one inside, one at the edge, carry the exact same information. This was astonishing. For the first time, holography was not just a poetic guess, but a mathematical identity. What happens in a higher dimensional space with gravity can be described perfectly by a lower dimensional theory without gravity. Space and time, depth and distance emerge from information on a surface. Physicists soon realized the power of this. Problems that were difficult in one description became easier in the other. A complicated gravitational puzzle in the bowl could be translated into a tractable calculation on the rim. A thorny quantum question on the rim could be solved by imagining it as a smooth gravitational picture in the bowl. The two worlds spoke to each other, each completing the other's sentences. For bedtime minds, though, the beauty lies not in the calculations, but in the image itself. Think of standing in a valley surrounded by mountains. You might imagine that the air and space within the valley are vast and independent. But now imagine that every detail of the valley's weather, every eddy of wind, every drifting cloud, is already written on the ridgeline. The boundary and the bulk are one story, told two ways. Maldacena's correspondence was a breakthrough not just for holography, but for the dream of quantum gravity, the search to reconcile Einstein's general relativity with the quantum world. For decades, the two great theories had stood apart, one describing the smooth geometry of space-time, the other the jittery behaviour of particles. Added CFT showed that they might be two sides of the same coin, related by a holographic duality. It is worth noting that our universe is not anti-de Sitter. We live in a cosmos closer to de Sitter space, with positive curvature, expanding outward like an inflating balloon. That means ADS CFT is not a direct description of our world. Still, it serves as a powerful laboratory, a proof of concept, a demonstration that holography can work exactly, not just metaphorically. And perhaps that is enough to let the imagination drift. Imagine again the bowl and its rim. The broth inside swirls with motion, but its every detail is encoded in the rim's pattern. Or think of a novel written on thin sheets of paper. The story feels deep, rich, filled with landscapes and characters, but it is ultimately encoded in flat ink on two-dimensional pages. The depth is real to you, but its origin is surface. As you let your eyes grow heavy, carry that thought, that the universe itself might be a story told twice, once in the bulk of space you inhabit, once on a distant boundary that encodes every detail. Two perspectives, one reality. And in that doubling lies a secret symmetry. Gravity and quantum, bowl and rim, depth and surface, all whispering the same song. Once physicists had begun to explore Maldacena's correspondence, the bowl and its rim, they noticed something striking. The duality was not just a clever way of rewriting equations. It seemed to tie the most delicate threads of quantum mechanics directly to the shape of space-time itself. In particular, they discovered that the strange, invisible bonds of quantum entanglement, those ghostly connections that link particles across distance, were mirrored in the very geometry of the bulk. To understand this, we turn to a deceptively simple image, a soap film. Imagine bending a wire into a loop and dipping it into soapy water. When you lift it out, a thin, shimmering film stretches across the frame. The film naturally takes the shape that minimizes its area, adjusting itself until it becomes as small as possible. If you tug the wire into new shapes, the film reshapes too, always finding the least area surface it can. It is delicate, but it obeys a strict rule. In the AD-CFT picture, something similar happens. If you pick out a region on the rim of the bowl, the boundary theory, you can ask, how entangled is this region with the rest of the boundary? The answer, astonishingly, is given by the area of a minimal surface that stretches into the bulk, like the soap film spanning a wireframe. The more entanglement, the larger the surface. The less entanglement, the smaller it becomes. This discovery, known as the Rutaka-Yanagi formula, was like finding a Rosetta Stone between two languages, the language of quantum information and the language of geometry. Suddenly the invisible probabilistic connections of quantum mechanics were written as visible, smooth shapes in space-time. Entanglement was no longer just an oddity of particles, it was the scaffolding of reality itself. Think about what this means in gentler terms. Entanglement is the way particles remain mysteriously connected, no matter how far apart they drift. It's like two dancers who, even when separated, still move in rhythm. Normally this seems like a curious detail of the quantum world, hidden in laboratories. But in AD-CFT, entanglement becomes monumental. The rhythm of those dancers shapes the very floor beneath their feet. Geometry itself is born from connection. Picture again the soap film shimmering in rainbow light. Its area is not random. It encodes the invisible relationship between two parts of the boundary. It is as though every bond of entanglement lays down a thread, and together those threads weave the fabric of space. The bulk is not just a stage, it is a tapestry, each stitch tied to a quantum connection on the rim. This idea resonates beyond mathematics. Consider your own life, the strength of your connections, the friendships, the family ties, the moments of empathy, shape the geometry of your days. Remove those bonds, and the structure of life collapses. Add them, and life gains texture, dimension, meaning. Physics seems to echo this truth. Connection is not decoration, it is foundation. Of course, in physics, the scale is cosmic. Entanglement between regions of a boundary defines surfaces deep in space-time. But the metaphor helps us sense it. The bonds we cannot see are the ones that build the world we walk through. It also adds a new layer to holography. In a traditional hologram, light interference encodes depth. In the cosmic hologram, entanglement encodes geometry. Surfaces in space are not arbitrary. They are records of how quantum systems are woven together. The bulk becomes a reflection of information flow, like a grand mirror of connection. And so, the story unfolds gently. Black holes told us that entropy clings to surfaces. Busso taught us that light defines boundaries for information. Maldacena revealed that gravity in a bowl is equal to quantum fields on the rim. Now Ryu and Takayanagi show us that entanglement, delicate, invisible, quiet, is the thread stitching it all together. As you rest, imagine dipping a frame into soap water and watching, the film stretch taut, glistening with colours. Imagine that film as more than play. It is a cosmic equation in disguise, a surface that tells the story of entanglement. Imagine that every shimmering curve in the bulk of space-time is a soap film, each one whispering how deeply the rim is connected. Perhaps the most calming thought of all is that geometry, something we usually think of as rigid and cold, may be born from something as soft as entanglement. The universe may be built not from stone but from threads, not from hardness but from connection. And that thought, like a soap bubble rising in sunlight, is both fragile and beautiful. There is a quiet wonder in realizing that the solid ground beneath your feet may not be so solid after all. We're used to thinking of space as a kind of stage, a floor that stretches outward, a backdrop for matter to dance upon. But in the AD-CFT picture, and especially through the lens of entanglement, a different story emerges. The stage is not built in advance. The stage is woven, thread by thread, Out of invisible connections, this idea is easiest to feel through fabric. Take a scarf, knitted carefully from strands of yarn. If you look closely, the scarf is not a solid sheet, but a lattice of interlaced threads. Remove enough threads, and the scarf begins to unravel. Pull a single string, and an entire section can collapse. The fabric's solidity is an illusion born of its connections. Without the threads, there is no scarf. Space-time, physicists suggest, might be the same. The smooth geometry we move through is not fundamental but emergent, arising from a vast web of quantum entanglement. Each bond between particles, each thread of information, contributes to the stitching of space. Pull those threads apart, reduce the entanglement, and the geometry itself weakens, frays, perhaps even vanishes. This thought is both profound and strangely comforting. It means that the deepest foundation of the universe is not hardness but relationship. Reality is not built of blocks but of bonds. And if you could look at space-time under a cosmic magnifying glass, you might not see bricks and mortar. You might see threads glowing faintly, woven into a tapestry of connections. To soften the image further, imagine a spider's web glistening with dew at dawn. From a distance, it looks like a delicate sheet, but step closer and you see it is made entirely of lines, threads crossing, joining, intersecting. Remove the threads and the sheet is gone. Space-time may be like that web, spun from entanglement. Physicists have begun to explore this in detail. In ADS-CFT, one can study how reducing entanglement on the boundary affects the geometry of the bulk. In some cases, tearing entanglement literally tears the geometry apart like pulling stitches from cloth. The smoothness of space, the very possibility of walking from one place to another, may depend on the invisible bonds of entanglement holding it together. It is a radical shift in perspective. For centuries we thought of space as absolute, a vast container within which matter resides. Now the whispers of holography suggest that space itself is born from information, from the way parts of a system share secrets with each other. Entanglement is not just a curiosity of quantum experiments, it may be the loom of the cosmos. This ties back gently to life itself. Our own days are woven from relationships. The texture of a community comes not from isolated individuals but from the bonds between them. A neighbourhood without connection feels empty. One bound by ties feels alive. The same truth, it seems, echoes upward into physics. Connection is structure and structure is space. It also redefines emptiness. A region of space that looks void may still be richly entangled, its geometry held together by bonds you cannot see. The silence of empty space may be less like nothing and more like a hidden chorus, each note tied to another, composing the fabric of reality. And so, holography takes us to a gentle but profound conclusion. Geometry is information, and information is connection. The bowl of ads with its rim of CFT tells us that depth is encoded on boundaries. The soap films of Ryuta Kayanagi show us that entanglement paints surfaces into geometry. And now, the woven scarf reminds us that space itself is a tapestry of quantum threads. As you lie here, perhaps with a blanket pulled over you, imagine that blanket as the universe itself. Every fibre is a bond, every knot an entangled pair, every weave a sign of structure. You're not lying under space, you are lying within it, part of the fabric, woven into the grand quilt of reality. And in that thought lies a quiet peace. The cosmos is not hard stone but soft thread. It is not built of walls but of relationships. And the more you look, the more you realize that to exist at all is to be entangled, to be part of the weave, to be carried forward in the fabric of space. By the mid-1990s, the idea that black holes carry entropy proportional to their surface had become widely accepted. Bekenstein's bold leap and Hawking's glowing radiation had tied black holes firmly into the world of thermodynamics, Yet a question lingered like an unfinished chord. Where does this entropy really come from? Entropy is, at its heart, about counting possibilities, the hidden microstates that lie beneath the smooth face of a system. For a gas in a box, those microstates are the countless ways molecules can move. For a deck of cards, it is the countless shuffles that still look like mess. But what about a black hole? What are its microstates? From the outside, it looks so simple. Mass, charge, spin, nothing more. Where could the hidden complexity reside? In 1996, two physicists, Andrew Strominger and Kamran Vafa, found a remarkable answer. Working within the framework of string theory, they studied certain kinds of black holes that were highly symmetric, existing in higher dimensional spaces. String theory, recall, suggests that the fundamental particles of the universe are not points but tiny vibrating strings, each note of vibration corresponding to a different particle. These strings can also form higher dimensional objects called branes, like sheets or membranes stretched through space. Strominger and Vafa realised that some black holes could be built from specific arrangements of strings and branes. Think of it like constructing a necklace. Each bead is a brane, each thread a string, and the way you arrange them creates a specific configuration. There are countless ways to arrange such beads and threads, countless microstates that from a distance all look like the same black hole. They set out to count these configurations. To their amazement, the number of microstates they calculated matched exactly the entropy predicted by Bekenstein and Hawking. Every tile on the horizon, every bit of entropy had a microscopic explanation in terms of strings and branes. The black hole's entropy was not mysterious after all. It was the statistical sum of its hidden stringy states. This was a triumph. For the first time, the surface law of black holes had a microscopic underpinning. It was as though a safe that once seemed sealed had revealed a hidden drawer full of neatly catalogued keys, each one corresponding to a possible configuration. The simplicity of the black hole's exterior hid a vast richness of interior possibilities, invisible from the outside but real in the language of string theory. To soften this for the imagination, think again of a necklace of beads. From across the room, all you see is a glittering circle. It looks uniform, featureless, just a loop of shine. But up close, you can see the pattern of beads, the specific sequence of colours, the knots of the string. Each arrangement is different, though the necklace looks the same from afar. Black holes are like that. From a distance, you see only mass, charge, and spin. But deep within, countless string and brane configurations provide the hidden pattern that explains the entropy. This insight reassured physicists. It suggested that the area law of black hole entropy was not a mysterious coincidence, but a natural consequence of microstates. Information they felt was not erased. It was simply hidden in the quantum complexity of the strings. Yet, it was also humbling. Strominger and Vafa's calculation worked best for certain supersymmetric black holes, idealized versions in higher dimensions, not the messy astrophysical ones formed from collapsing stars. It was a proof of concept, not a universal answer. But proofs of concept matter. They show that a path exists, even if the road is narrow. And for bedtime minds, the beauty lies less in the technicalities and more in the metaphor. Black holes, once seen as ultimate erasers, were revealed as keepers of secrets. Their entropy was not a blank wall, but a ledger filled with microscopic entries, each one a hidden possibility. Strings, the tiny vibrating notes of the universe, provided the alphabet in which those entries were written. So, as you let your eyes close, imagine a necklace of infinite beads, each strung in countless patterns. From afar it looks the same. Up close it is a universe of variation. That necklace is the black hole's entropy, a silent testimony that simplicity on the outside hides infinite richness within. There is something hauntingly beautiful about entanglement. Two particles created together can remain mysteriously linked, no matter how far they drift apart. Measure 1, and the other responds instantly, as though distance doesn't matter. Albert Einstein once called it spooky action at a distance, and for decades physicists puzzled over how such invisible threads could stretch across the cosmos. In 2013, two great physicists, Juan Maldacena and Leonard Susskind, suggested a radical possibility. Perhaps those invisible threads are not abstract at all. Perhaps entanglement is geometry. Perhaps every entangled pair is connected by a tiny wormhole, a bridge through space-time itself. They called this bold idea ER. EPR. The initials carry history. ER refers to Einstein and Rosen, who in the 1930s described theoretical tunnels through space-time, now called Einstein-Rosen bridges, or wormholes. EPR refers to Einstein, Podolsky and Rosen, who in 1935 described the paradox of quantum entanglement. Maldacena and Susskind combined the two into a single equation. Entanglement and wormholes are two faces of the same phenomenon. To make this softer, imagine two clocks sealed under glass domes on opposite ends of a table. At first, you think they're separate, each ticking independently, but no matter how far you move them apart, their ticks remain in perfect sync. It feels uncanny, as though some invisible wire connects them. EPR suggests that the wire is real, not a physical thread you can see, but a wormhole hidden in the folds of space-time. The clocks are not merely coordinated, they are linked by a bridge. Of course, these wormholes are not the science fiction tunnels you can fly a spaceship through. They are subtle, non-traversable connections, doorways that exist only as correlations, not as highways. You cannot send a message through them, cannot leap across galaxies in an instant. But still, the idea is profound. It says that geometry and information are inseparable. Entanglement, once thought of as an odd feature of quantum mechanics, may actually be the stitching that binds space-time together. Picture again the woven scarf from earlier. Each crossing of threads gives the fabric strength. In Giestian's EPR, each entangled pair is such a crossing, such a knot. Remove enough of them, and the fabric of space-time might unravel. Add them, and the fabric holds. This thought reshapes how we see even the emptiest places. A vacuum may look barren, but it is filled with entanglement, pairs of particles bound together across distances. And those bonds, invisible yet fundamental, may be the reason space itself holds together. It also deepens our view of black holes. When two black holes are maximally entangled, EPR suggests they might be connected by a wormhole. The entanglement is the geometry is the entanglement. The two languages are one. For a bedtime mind, the poetry is enough. Imagine sitting under the night sky, stars scattered like lanterns. Invisible threads stretch between them, threads you cannot see but that hold the cosmos together. Some threads connect particles, some connect black holes, some connect regions of space itself. Every bond is both a whisper of information and a stitch of geometry. And perhaps this echoes something familiar. In human life too, the bonds you share with others are not visible threads, yet they shape the geometry of your days. Friendships, love, memory. None are physical bridges, but all create the structure of your world. Perhaps EPR is physics' way of saying the same. Relationships are real. They're not decorations on reality. They are its foundation. The conjecture is still debated, still explored, still unfolding in new mathematics. But whether or not wormholes truly hide in every entangled pair, the idea leaves us with a gentle truth. The universe is stitched by connection, and every time two particles share a secret, they may also share a bridge, invisible but enduring, weaving space-time into the soft tapestry of existence. For decades, the black hole information paradox sat like a riddle no one could solve. Hawking's radiation seemed to erase information forever, while quantum mechanics insisted that information must be preserved. Physicists argued fiercely. Some thought perhaps quantum theory would have to bend. Others insisted black holes must somehow keep the information hidden. The debate stretched on, unresolved, a paradox at the heart of physics. Then, in the late 2010s, a breakthrough came. Using the tools of holography and quantum information, physicists discovered that the paradox could be softened, even resolved, at least in certain models. The key was a strange new concept called islands. To understand this, we need a story. Imagine recording the sound of a campfire on an old cassette tape. At first, the tape fills with crackling noise, chaotic and featureless. It feels like information is being lost, as though the story of each spark and ember is dissolving into static. But as you keep recording, patterns emerge. The crackling begins to tell a story, rhythms repeat, the fire's life becomes encoded in the sound. What seemed like random noise at first is eventually revealed to contain structure. The information was there all along, waiting for the right perspective to recover it. Black hole radiation works similarly. At first, the radiation looks thermal, random, meaningless. The entropy of the radiation increases steadily, as though information is being destroyed. But if you wait long enough, something shifts. The entropy reaches a peak and then begins to fall. The curve of entropy over time, known as the Page curve after physicist Don Page, shows that information comes back. It is not erased but scrambled, encoded in ways we don't yet fully understand. For decades, no one knew how to calculate this curve from first principles. Hawking's calculations stubbornly gave a rising line, never bending down. Then, in 2019 and 2020, several groups of physicists found a way. By considering quantum effects more carefully, specifically subtle geometric contributions called replica wormholes, they discovered that black hole radiation entropy does indeed follow the Page curve. The trick was the islands. In these new calculations, certain regions inside the black hole must be included as part of the outside radiation system when computing entropy. These regions, called islands, expand as time goes on, eventually accounting for all the information that seemed lost. In other words, the horizon is not a perfect wall. Information inside can still be counted as part of the outside if you know how to look. It is a strange idea. Boundaries blur. What seems inside may belong to the outside. But in the mathematics, it works beautifully. The entropy curve rises, peaks, then falls. Just as Page predicted, just as unitarity demands. Information is preserved. To soften this, imagine a child blowing soap bubbles in the yard. Each bubble seems separate, a closed sphere. But as the bubbles drift and merge, you realize that what was once inside one bubble can become part of another. The surface you thought was a firm boundary is more flexible, more porous than it first appeared. The islands in black hole physics are like that. New regions join the outside, allowing information to be seen where once it seemed lost. This modern result does not mean the paradox is fully solved. These calculations work best in toy universes, adds space-times where holography is sharp and tractable. Our own cosmos, with its positive curvature, remains outside the exact reach of these tools, and the details of how information escapes a black hole in practice are still debated. But the moral is clear: information is not destroyed. The universe keeps its promises. For a bedtime mind, perhaps the most soothing image is the Page curve itself. At first, entropy rises like the crackling of a fire, the scattering of sparks into night. Then it bends gently downward, like a lullaby easing into calm. Information, like memory, returns, not as the same story, but as a reassurance that nothing is truly lost. So as you drift toward rest, think of a tape recorder humming beside a fire. Think of the hiss and crackle filling the tape, and gradually giving way to patterns. What seemed like noise becomes music. What seemed like loss becomes recovery. In the same way, black holes, once thought to erase information forever, now seem to preserve it, weaving it back into the universe with subtle care. And with this, the long paradox softens. The glow of Hawking radiation no longer threatens the consistency of physics. The page curve bends, the islands appear, and the story continues. What once looked like erasure now looks like a different kind of writing, hidden but enduring, waiting for us to learn the language to read it. So far, our story has unfolded inside a bowl, anti-de Sitter space, or ADS, with its inward curving walls, gave us a perfect stage for the holographic principle to shine. On its rim lived a quantum field theory. Within its bowl lived a world with gravity, each mirroring the other like two reflections in a still pond. For physicists, ADS was the proof of concept, the place where the holographic principle wasn't just a metaphor, but a working identity. But as comforting as that bowl is, it is not our home. Our universe does not curve inward like a soup dish. It stretches outward like a balloon, swelling gently as time goes on. Galaxies drift farther apart, the night sky grows quieter, and the expansion accelerates. This is the geometry of a de Sitter universe, not anti-de Sitter. We live not in a bowl, but on a balloon, its surface swelling larger with every moment. Imagine drawing tiny stars on the surface of a balloon. As you inflate it, the stars move farther apart. They are not flying away under their own power. It is the stretching of the surface itself that carries them. This is our cosmos, galaxies painted on an expanding balloon, each carried away by the swelling of space-time. By contrast, ADS is like a bowl with steep sides, objects rolling inward, boundaries looming above. The two shapes could not be more different. This difference matters. The elegance of ADS-CFT rests on the bowl's geometry. Its negative curvature ensures that signals bounce back, boundaries hold firm, and information is neatly encoded on the rim. In our balloon universe, with its positive curvature, light rays do not return. They drift outward, horizons form, and information seems to fade beyond sight. It is not obvious how to draw the same sharp holographic correspondence. Still, physicists have tried. Andrew Strominger and others have proposed a version of holography for de Sitter space, sometimes called a DS-CFT. The idea is similar, that a field theory might live on the boundary of de Sitter space, encoding everything within. But the details are murkier. For one thing, our universe doesn't have a clean, fixed boundary, like the rim of a bowl. Its horizons are shifting, tied to the expansion of time itself. Where exactly should the holographic code be written? On the infinite future? On the cosmic horizon? The answers remain elusive. To bring this back to gentler ground, think of trying to keep a diary while riding in a hot air balloon. The balloon rises, the wind shifts, the scenery changes. You want to record everything you see, but the horizon keeps moving, and what was once near vanishes into distance. In a bowl, the scenery is enclosed. You can take your time, knowing nothing escapes your view. On a balloon, the view is open, expanding, and always slipping away. Writing a complete diary feels harder. This is the challenge of holography in our universe. The code may exist, but its pages are harder to pin down. The cosmic diary is written on a horizon that drifts with the expansion of space, always moving farther, always changing shape. Yet there is beauty in this uncertainty. Even without a perfect correspondence, the idea of holography continues to inspire. It suggests that information is never truly lost, even in a universe where galaxies drift away and horizons recede. It hints that the expanding balloon carries a script on its surface, subtle and shifting, but present nonetheless. And perhaps there is comfort in the metaphor itself. When you look at the night sky, you're gazing at stars painted on the balloon of space, their light stretched into red as the fabric expands. When you listen to the silence between galaxies, you are hearing the breath of expansion. When you imagine the entire cosmos swelling outward, you're seeing the balloon's surface grow. If holography whispers anywhere, it may be on that swelling skin, where the universe keeps its hidden ledger. So, while we cannot lean too heavily on the bowl of ADS, we can still dream with the balloon of DS. Strominger's proposals and others remind us that physics is not about certainty alone. It is about extending metaphors, testing them, and letting them guide us into new possibilities. Perhaps one day, DCFT will stand as firmly as AdCFT does now, or perhaps a different principle, more suited to our balloon universe, will emerge. For now, let the image settle gently, a bowl curved inward, where light returns and holography works with precision, and a balloon curved outward, where galaxies drift and horizons shift. We live on the balloon, not the bowl. And though our stage is different, the lesson endures. Boundaries matter, surfaces whisper, and the universe still invites us to read its hidden script. Up to now, our story has been woven from theory, mathematics, metaphors, and careful reasoning. Black holes hinted at surfaces, entropy bounds whispered of limits. AdCFT showed a precise example in a curved bowl of space-time. But for all its beauty, theory alone leaves a lingering question. Is any of this real for our universe? Physicists, ever curious, have tried to listen for holography in the hum of nature. One bold attempt came from Fermilab, just outside Chicago, in an experiment nicknamed the Holometer. Its purpose was simple in spirit but profound in ambition, to see if space-time itself might be grainy, pixelated, like a holographic screen. The idea was that if the universe is holographic, then at the tiniest scales, around the Planck length, there might be a kind of jitter, a noise, as if reality itself flickers like a projected image. This noise, sometimes called holographic noise, would be unimaginably subtle, but in principle detectable with extremely sensitive instruments. The holometer used twin interferometers, machines that split beams of light and recombine them to detect tiny shifts, smaller than the width of a proton. If space-time itself had a holographic jitter, the beams might wiggle in unison, revealing the universe's hidden grain. For months the holometer listened, poised like an ear pressed to the static of reality, waiting for a whisper. And what did it hear? Silence. Or rather, the usual hum of the universe, thermal vibrations, electronic fuzz, but no sign of holographic noise, no correlation that pointed to the universe as a hologram. The experiment was a null result. At first, that might feel disappointing, like standing in a quiet room waiting for music that never comes. But in science, silence is as valuable as song. A null result doesn't mean the idea is wrong. It means reality is subtler than one particular model. Holography may still be true in some deeper form. It just doesn't reveal itself through this kind of static. To make this gentler, imagine tuning an old radio late at night. You turn the dial slowly, listening through the crackle of static, hoping to catch a faint melody from a faraway station. Sometimes you hear voices or music hidden in the noise. Other times, nothing but hiss. The holometer was such a radio, scanning space-time for a signal. This time it heard only static. But that doesn't mean no song exists. Perhaps we were tuned to the wrong frequency, or perhaps the music lies beyond our current reach. This honesty is important. The holographic principle is still unproven for our universe. AdS-CFT is exact but belongs to a bowl-shaped cosmos, not our balloon-shaped one. Experiments so far have found no direct evidence of holography, and yet the principle continues to inspire because it ties together so many threads: entropy, black holes, quantum information, geometry. Even without proof, it feels like a compass pointing towards something real. Science often moves this way, with theory running ahead like a scout and experiment following patiently behind. Sometimes the scout finds a true path, sometimes it circles back. But even when no direct evidence arrives, the journey reshapes our understanding, widening our imagination. For bedtime minds, perhaps the most soothing thought is this: uncertainty is not failure. the silence of the holometer is not a dead end. It is a pause, a reminder that the universe does not give up its secrets easily. And in that pause, wonder remains alive. So picture yourself again with that quiet radio, the dial glowing faintly in the dark. You listen to the static, hoping for a faint tune. Even if no melody arrives tonight, the act of listening is itself beautiful. The hush of the room, the anticipation, the sense that beyond the static lies something waiting, that is its own kind of music. The holographic principle, at least for now, is like that. It may be the true story of our universe, or it may be a chapter in a larger tale yet unwritten. Either way, its whispers have already changed how we see the cosmos. And sometimes it is enough to rest in the mystery, letting silence be the song. We have journeyed far tonight, from steam engines and entropy, through black holes and horizons, to soap films and holographic codes. We have followed whispers into bowls and balloons, into strings and wormholes, into islands where information hides. And yet, at the edge of this long path, a truth waits quietly. We do not know if the universe is truly holographic. The principle is beautiful. It ties together entropy, geometry, and information with a grace that feels inevitable. But beauty is not proof. For all its elegance, holography remains a guide, a map sketched by theory rather than confirmed by experiment. Maps are useful, but they are not the territory. Imagine unfolding an old paper atlas on your lap. Rivers are drawn as blue lines, mountains as shaded triangles, cities as dots. The map helps you understand where things might be, how they connect, how far you must travel. But the map is not the land itself. The rivers on the page do not flow, the mountains do not rise, the cities do not sleep. The map is a tool, not the world. The holographic principle may be such a map. It may sketch, in simplified form, the way entropy and information shape space-time. It may point us in the right direction, even if the real territory is more rugged, more complex, more surprising than we imagine. And that is not failure. That is how science lives. Sometimes the questions matter more than the answers. When you ask, is the universe two-dimensional at heart? You may never find a simple yes or no, but in asking you discover new connections, new insights, that black holes are thermodynamic, that entanglement builds geometry, that information may be as real as matter or energy. The value lies not only in arriving but in travelling, not only in proofs but in perspectives. There is humility here, and perhaps comfort. The universe does not owe us clear explanations. It does not open its diary at every page, but it gives us glimpses, enough to wonder, enough to guide, enough to keep walking forward. Think of a lighthouse in the fog. Its beam does not reveal the entire coastline. It gives you only a sweep of light, a partial view. But that sweep is enough to steer by, enough to remind you that land exists beyond the mist. The holographic principle is such a lighthouse. Its light is partial, incomplete, but steady. It guides, even if it does not yet reveal the full shore. And perhaps this is a truth that reaches beyond physics. In our own lives too, we often live with partial maps. We do not always know where we're headed or why things happen, or what lies beyond tomorrow's horizon. Yet we move forward, guided by glimpses, by questions, by faint beams in the fog. Uncertainty is not an enemy. It is the condition of exploration. So tonight, let yourself rest in that space. You do not need all the answers. You do not need the map to be perfect. The questions themselves are enough. They remind you that you are part of a vast story, a story still unfolding, a story that values curiosity as much as certainty. Perhaps the greatest boundary of knowledge is not the edge of the cosmos, but the edge of our need for closure. To accept mystery is to make peace with the fact that the universe is larger than our understanding and always will be. And that is not a limitation, it is a gift. for it means there will always be new questions to ask, new connections to find, new metaphors to dream. The story does not end. It simply continues, wave after wave, like the tide brushing against sand. So let this thought be a gentle anchor. Holography may be true, or it may not. But the journey toward it has already given us new ways of seeing, entropy as probability, black holes as thermodynamic creatures, geometry as woven entanglement. Even if the final answer slips away, the path itself has been rich, and in that richness you can rest. The boundaries of knowledge are not walls but horizons. They do not confine, they invite. And as you drift towards sleep, you may find comfort in knowing that some questions are not meant to be solved tonight, but to be carried softly into tomorrow. And so we arrive at the quiet end of our journey. We have walked through steam and entropy, through black holes and horizons, through soap films and strings, through wormholes and islands. Along the way, we have seen the universe not as a static stage, but as a story, one woven from probabilities, from connections, from information whispered on boundaries. The question that brought us here was deceptively simple. Is the universe actually two-dimensional? And the answer, after all these wanderings, is just as simple and just as profound. We do not know. There is no proof, no final verdict, only clues, threads and glimpses, woven into patterns that suggest but do not confirm. Yet perhaps that is enough. The clues themselves are beautiful. They tell us that entropy grows not with volume but with surface, as though the universe prefers to write its secrets on skins. They tell us that black holes, once thought to be destroyers, are careful accountants, keeping ledgers in mosaics of plank-sized tiles. They tell us that entanglement is not just a curiosity, but a loom, weaving geometry itself into being. They tell us that wormholes and islands may restore what once seemed lost, preserving information in ways stranger than we imagined. All of this forms a tapestry of hints, a map, not the territory, a melody, not the full symphony. But sometimes a melody is enough to stir the soul. To settle this in gentler terms, imagine lying in a field at night. Above you, stars shimmer like faint candles, their light crossing unimaginable distances to reach your eyes. You cannot touch them, cannot prove their depth, yet you feel them as real, their presence undeniable. They might be thought of as distant holograms, projected onto the dome of sky. Whether or not that dome is literal, the effect is the same. The surface holds the depth, the boundary holds the story. Or think of a dream. In the dream, you walk through landscapes that feel solid, mountains rising, rivers flowing. Yet when you wake, you realize the dream was woven from signals on the thin surface of your sleeping brain. Depth was an illusion, yet it carried weight, meaning, beauty. Perhaps the universe is like that. A dream woven from boundaries, a story projected from surfaces. And so, we return to our question. Could our three-dimensional world be a hologram, a projection of information on a two-dimensional boundary? We cannot say for certain. But in chasing the question, we have learned that entropy, information, and space-time are entwined. We have learned that the universe is more relational than substantial, more woven than built. We have learned that mystery itself is part of the fabric. There is calm in that. You do not need the final answer tonight. You do not need the proof. What you need is the wonder, the sense that you live inside a story larger than comprehension, a story that invites you to rest within it. So as you let your eyes grow heavy, picture the stars again, scattered across the night sky. Each one might be a projection, each one a coded spark on a cosmic boundary. Together, they form a dome of light, a quiet hologram of infinity. Beneath that dome, you lie, small but part of it all, woven into the same fabric, carried by the same threads. whether the universe is truly two-dimensional or whether the holographic principle is only a metaphor, the wonder remains. You live in a cosmos that is vast, mysterious, and tender enough to carry your questions into the night. And as the questions drift outward, like ripples on water, they leave behind a hush, a quiet spaciousness in which rest can find you. So, breathe deeply. Let the mystery settle around you like a blanket. The stars shimmer, the boundaries whisper, and the universe hums softly. A lullaby of entropy and information, of questions and connections. Sleep peacefully within the calm wonder of not knowing.